Welcome to this video on the consumer problem. In this video, I will recap how we do optimization in Python. I will talk a bit about how we can do it either with loops or much better with an actual optimizer, and even how you can actually write your own optimizers to understand a bit more what happens inside these optimizers. Specifically, we will look at a gradient descent optimizer. And then at the end, we will look at an actual consumer problem. In the notebook, from types, I will be using the simple namespace. I will explain what that is if you haven't seen it before. I will be using NumPy, and I will be using optimize from SciPy, and I will be using matplotlib with some settings. But okay, fine. So we have this set up. So probably the two most important tools you have learned is to solve optimization problems, either with scipy.optimize.minimize for multi-dimensional problems, or scipy.optimize.minimize scalar for single-valued functions. And similarly, how to solve equations with the root and the root scalar, again from scipy.optimize. It's a bit of a black box probably for you how this is working. More details will come later in the course. But it's a good idea to compare it with something that's perhaps easier to understand, so you get a bit more feeling for what's going on. To do this, let us consider a simple maximization problem, where we simply want to maximize some function, and let's say that this function is minus 3 times parentheses x minus 2 squared plus 1. So if you take the derivative here, it's clear that you get that this will be equal to 0 at x equal to 2, and you can sort of see that then this will be 0, and otherwise it's negative. So this is where it's maximizing. So it's easy to solve sort of even in your head, but it can be useful to see how we can do it in many different ways numerically. So let's define this function. The simplest thing you could do is you can sort of say, okay, let's try out some values, right? So let's try out values, 100 values between minus 10 and 10, and let's find out what is the function values at these. We haven't seen anything, so let's start by saying the best we have seen is minus infinity, and we don't know what the best is, so that's just not a number. Then we loop through all the x's, and enumerate them, and we calculate what is the function value, and we save that. If it's the best yet seen, then we save that. So if we do that, then we can see that we get that the best thing with a loop is 0.998 at x equal to 1.919, so on. That's not quite right, we know. So how can we improve it? Yeah, we can improve it by simply adding one more, or adding one more zero, or doing more and more searches. And in this way, we can get closer and closer. But it also begins to take a bit of time to do it, because we need to loop through a lot of different things. So let's look a bit more into it when we had this 100. Then we can plot what's actually going on here, and we can plot that. Okay, we can see that we get something that's very close to what the actual maximum is, but we're not quite there as we know. So let's use some optimizers instead. The first thing we could do is we could use the minimize scalar, and the easiest way to do that is sort of to create an objective function for the minimize scalar, which we think of as a function of x, but then minus this function, because this would be a minimizer. So given that we want to maximize, we're doing it on the minus of the function. And here the input is just the scalar value of x. And then we put it into minimize scalar. I choose a bracket, and I use the Brent method for doing it. And then we pull out what is the x and what is the function value, and I take a minus such that we get close to that. And you can see that this exactly gets to 1 at x equal to very fast. So this is just better than what we had before. Of course, it's a bit more complicated code, but we get the right result very, very quickly and very precisely. Instead of minimize scalar, you can also use minimize, That's a slightly different interface. Here it assumes that your input is a vector. So now you will guess on a vector, and I will just guess on 0. And it will only be one input here. But now when I create my objective, I will say it's a function of x, where x is a vector, and then I put the first element of x into the function. Take the minus as before. And here I take the objective, I put in the guess, and for a method I choose nil meet, which is a simple way of doing it. And I can run this, and again this works. So this is just different ways of achieving the same goal. I could also say, okay, let's find the derivative. I found that before. Let's define that as a function, and then let's use root scalar to solve for when is this derivative 0. And the setup of the code is very similar. I define an objective function. Now I don't need to be any minus here, right? Because we're just finding the 0. We don't care about whether it's optimizing or minimizing or whatever. We're just finding a 0. And now we use again the same bracket, and we use the bisection method for doing that. And now the result structure has the result in .root, while up here it has it in .x. But otherwise, the interface is similar, and we again get the right result out. Again, there's a multidimensional version of this, where we have a vector that we guess on, and when we set up our objective function, we go into this vector. And now we have to choose another method than the bisect method, and can, for example, use this hab method, and again we solve it exactly. So there's many different ways we can solve the same problem in, and it's good to know them all, because sometimes there might be benefits, or you might have trouble getting one of them to work, and then you can try out another one. But let's try to understand a bit more about what happens inside these calls here. This is some rather complicated code, so we will not look at it, but we will sort of think about how could we do something similar ourselves. And specifically, we will consider a minimizer, which is a gradient descent minimizer. And the way that works is in the following steps here. So this is describing an algorithm for how to do the minimization. It starts by saying, let's choose some tolerance, which should be a small number larger than 0, and let's choose some step size, which should be a positive number and not too large. And then some initial guess, x0, and let then set a counter equal to 0. Then we will compute the function value at this point, and we will compute the derivative approximately by calculating the function value at a bit larger x, and taking the difference and dividing with the change in x. If we now have something where the derivative is very small, then we will stop. If it's smaller than this tolerance, then we will stop, and we will be happy. If the absolute value is small, because then we have almost found a point where we are at an extreme value for this. Otherwise, we will compute a new guess down the hill. So that is, we will say, okay, what is our current guess? We will say, okay, we will take minus and then a step size that we have chosen, and then this derivative. So if we have a positive derivative here, and we want to minimize something, then we should sort of go towards a lower value. So we need to go for smaller x. So that will be the step size times the positive derivative. We should subtract that from our x, and then we will get a new guess. Then we will update our counter, and we will return to step 2, and we will continue doing that until our algorithm stops at this point 3. So let's see how that looks in code. So this gradient descent function here takes in a function, it takes in an initial guess, and it takes in the step size when we do our search. It takes in a different kind of step size for when we do the numerical derivative. It takes in a maximum number of iterations, and it takes in a tolerance. and then it will return the minimum, the function value at the minimum, and all the trials that has been done. So for initialization, our first step sets x equal to our initial guess, sets the number of the counter equal to 0, and it allocates our list for all the trials. Then, while we are less than the maximum number of iterations, we compute the function value, we compute this numerical derivative, and we save all these things as a dictionary with x, fx, and fp in our trials. Then we check our convergence. First we print out our counter, our x, our f, and our f prime. And if our absolute value of fp, the numerical derivative, is less than the tolerance, then we break. Then we're happy. Then we're done. Otherwise, we do this updating step where we subtract alpha times the derivative, and we update our counter, and we continue. So note that it's important to update the counter, because otherwise this could run infinitely, and it's of course central to have the updating step such that the x actually changes. So let's try to do that, and let's try to do this with a bit more complicated example, where the function that we want to maximize is minus sine of x plus 0.05 x squared. We will look at how that function looks in a bit. Let's say we guess at 0. We put in our f function here, our objective function, as what we have, and then we call our thing here, and we start with the counter 0, and we set x equal to 0, and we set find the function value of 0 and a derivative of -1. So now, according to our gradient descent here, then we will have a new, because this is not close to 0, so we will have a new value for x, and we will continue to calculate the f and the f prime, and we will have a new value for x, and we will continue doing that until at some point the derivative becomes smaller and smaller, and sometimes it's very small, and it will be lower than our tolerance, and we will say that this is our result. Okay, let's then print this. This is some function for printing that. It's not too important what it does. Let's just run it, and then you can see that our illustration is like this. So we can see that our starting point was here, and then it converts to this one down here. So here you see a couple of things. You can see how it converges by each iteration. It sort of takes some steps. So here it knows that the derivative is negative, and it's trying to minimize such that it goes down the hill, then down towards this one here. And actually I misspoke up here. I think what I meant to say actually was that we want to minimize this. So we can just quickly go in and change this. So then now we have changed the problem so that the code is right. So this is basically how it works. And we can see sort of for each iteration, we can see that our x value increases from 0 and upwards towards the result. And we can see that the derivative of x goes from -1 to 0. So this is basically how all optimizers work. They have this structure here. They might differ in how they take steps. They might differ in exactly what the termination criteria is, but this is basically what happens. It's much better to use optimizer uses written by someone else, because we might have written something wrong here. There might be something that's not that efficient to do, but it's a good thing to try to understand what's going on here, because then you will have, I think, sort of a more secure feeling when using optimizers everybody else has run. Okay, one thing I want you to pause the video and think a bit about is, can we guess on another initial value of x? Try to plug in another value and let's see what happens then. Okay, you should have done it yourself and thought a bit about why that was, and let me now do it here. So let's say that I guessed instead on -6. minus 5. You can see that it guesses on that and gets some derivative, and it's okay. It's finding a result. Oh, this result look different. Okay, so what's happening when I do this plot? Okay, so I started at minus 5, and then it converges to this thing here. Okay, so it didn't. How should it know that this is not the global minimum here? That there is a global minimum here? It couldn't. It cannot know that without without actually trying something over here. So if we start here, then it will convert to the first local minima it can find. And this is a general problem with optimizers, is that they will find local minima and not necessarily global minima. So it's always good to try out with different starting values and see whether you get the same result. Then you're more secure that you actually have found a global minima. But this is an unavoidable problem. There is sort of more general ways to handle it, which we'll talk about later in the course, but just so you know that this is a problem you should always be aware of. Okay, so let's now turn to a consumer problem. And I want to consider a consumer problem where the consumer takes some prices and income as given, and then it chooses consumption of 2 goods, and then there will be this utility function here, which sort of is a version of the CES utility function. And now the goal will be that we will create a model class to solve this problem. And we want model to be a class, and we want model.par to contain all our parameters, for example, the value of alpha, and we want model.solve to contain the solution, for example, model.solve.x1. So that's the thing that we want. And that's where these simple namespaces come in. It's very similar to a dictionary, but instead of but we use par.alpha instead of par square brackets and then a string value of alpha. So if I set up my simple namespace and I do the alpha and the sigma, then it simply looks like this. So this is very simple to write. You can always access sort of a dictionary interface of the simple namespace if you want to. So here I loop through it as a dictionary and print out the key and the value and get exactly the same thing. But yeah, I like this. I think it's a clear way to write the code. Okay, so let's define the utility function. And I want the utility function to be something that takes in the model and the actual choices. And from the model, I can derive what are the parameters. And then I can calculate the 2 parts of the utility here, and I can calculate the overall utility. So that's simple, just using the formula that was up here. Okay, so let's define this function. Then let's define a solve function where we take in the model, we unpack the parameters and the solution, and we define an objective function. And we want the objective function to be a function only of a vector of our consumption choices, which should go into our utility function, the first and the second value of the vector. Again, we do use the minus because we'll be using a minimizer. So we want the negative of utility. Then I will use something that can actually handle constraints and bounds. And the way I will do that here is that I will say, okay, let's specify our budget constraint as a function of our consumption choice. And then let's take our income minus what we spent on the first good and what we spent on the second good. If this is a negative number, then the budget constraint is violated. So that will not be allowed by the optimizer we will be using. And then I will specify this as a constraint by writing this a bit clumsy way, but you have a tuple where you have a dictionary and you say that the type of constraint you have is an inequality constraint, and the function that defines this is this budget constraint function. And then I will put in bounds saying that you can never consume more than a small number up till consume putting everything in on that and nothing on the other, and the same thing for the second good. I add these small numbers here, so that's 10 to the power of minus 8, right, to avoid ever having x1 or x2. And that's because if you look in the utility function, you will be raising it to a power, and it might not be good to have a 0 in that. And then I say, okay, let's guess on us using equal amounts of each good, and let's then call the minimize from optimize on this objective, which is initial guess. And now I will use this method, the SLSQP method, which can take in both bounds and centrally also constraints, specifically the budget constraint up here. I will run that, and then I will get the result of the first good and the second good, and I will calculate utility. So I can define this function as well. So now we have defined utilities, and we have the utility function. We have defined how to solve it. Now we need to put everything together. And the way I do that is I use a class. I call this a consumer class, and I say when you set up this class, then you should define the parameters, and they should be as follows. So the alpha and the sigma are various parameters in the utility function, and so on. I think I've added in a mu here that's not really needed, so let's maybe just delete it and see whether it still works. So I define this class, I put in the parameters and the solution, and I put in the utility function and the solution function as methods in this class. And now when I call the consumer class, I want to create an instance of it. I want to create a consumer called Jeppe, and I want to solve Jeppe's problem. Then I can do it like this. It sort of creates the problem, creates the model, solves the consumer problem, and prints out what is the optimal choices for the first and the second good, and what is the utility. So note when this is called, then this function up here, the initialization function initialization method is called. So when you have this, then you have defined all of these parameters, and you can solve it. So again, this puts everything nicely together, and creates a good structure for your code. Finally, the way of doing it this way makes it very easy to sort of loop over changes in value. So here I loop over alpha, to consider various values for that, put it into the Jeppe consumer, solve Jeppe's problem, and see what happens to the solution. So we can see here when alpha increases, then I consume more and more of the first good. So that is sort of clear, because that sort of is involved in the weight that we put on the first good inside the utility function here. Okay, finally, what I want you to do is I want you to try to create another consumer with some parameters of your choice and solve the problem that this consumer faces. Thank you for now.